Hi everybody, and welcome to exercise 1. In this video we will be looking at the matrix in part II here. Okay, this is the same exercise that we did in the first video of taking a matrix and first trying to determine what the eigenvalues and a basis for each eigenspace are. Okay, now we're going to discover that the algebra in this one, the technical details get a little bit complicated, so I'm gonna be working through part of the algebra steps, but then using technology to kind of finish the problem. And I hope that when you encounter problems like this, you'll do the same. Okay, so starting with eigenvalues here, okay, we need to look at the matrix A minus lambda I and take its determinant. So let's write down what that would look like. Okay, and you might notice, you can already see signs of trouble here if we wanted to do this by hand. There are no zeros in this matrix. So taking the determinant of this matrix, this would not be a pleasant thing to do. There'd be a lot of writing out, and you could do it by hand. It does factor, but it would take some time. Okay, so it's at this point, I would take out a calculator or take out Mathematica or maybe Wolfram Alpha or something like that. There are a lot of programs out there that can do a determinant like this for you. Okay, and factor the characteristic polynomial, and if you do that, you'll discover that this comes down to that. Okay, like I say, it takes a lot of work if you did it by hand to get there. So we can look at that and see what our two eigenvalues are. 3 and -1 it looks like. So we'll look at those separately, starting with 3. Okay, so our coefficient matrix would become, if we plug in 3 for all of those lambdas, 1, -3, 2, 1, -3, 2 again, and then -1, 3, -2. Okay, kind of nice what happens if you do row operations. Okay, we'll leave that first row the same, and then notice that we get 2 rows of zeros. Okay, so in this case we've got just one pivot position and 2 free variables. So if we let x2 be t and x3 be u, then we can solve for x1, and we're going to get 3t minus 2u. Okay, so to get eigenvectors, we've got 2 free variables, so we'll use kind of that standard technique of kind of making one of the free variables 1 and all of the other ones 0. So if we let t be 1 and u be 0, that's going to lead us to an eigenvector that looks like 3, 1, 0. Okay, and if we flip it around, make t 0 and u 1, that's going to lead us to an eigenvector of -2, 0, 1, it looks like. Okay, so for lambda 1 equals 3, we got 2 linearly independent eigenvectors, and we're ready to move on and look at the other eigenvalue, which is -1. And let's see what happens if we do that. So if we plug -1 into our matrix, we're going to get a 5, -3, 2 in the first row, then a 1, and a 2, and then finally -1, 3, and 2. Okay, and again, here's a situation where we could do these row operations by hand. Okay, this wouldn't be all that hard. Well, and actually, I'm going to go ahead and do it, because I think we can handle this. It would be okay to use technology as well. I'm going to do a little bit of row switching here first. Maybe take that second row and move it up into the first position. Okay, and then finally, we've got -1, 3, 2 down there. Okay, and let's see what we can do here. So if we take -5 times the first row and add it to the second row, we are going to get to there. Okay, if we add the first row to the third row, we're going to get that. And you can kind of see what's coming now. The second and the third row are now multiples of each other, so we're going to get a row of zeros. Okay, and I'm going to go ahead and divide the second row through by -8, just to make those ones. Okay, and there's a matrix that's in echelon form. Okay, and this time we get 2 pivot positions, so we've got 1 free variable. Let's make that free variable t. Okay, and if we solve for the other ones, let's see. x2 is going to be -t, and x1, okay, if we do the algebra here, is going to be -t minus -2t, which is -3t overall. Okay, oh, wait a minute. I think I didn't do that right. Hang on a second here. Back up. I see I made an algebra mistake. So x2 is actually -t. Okay, and if we back up and do x1 again, that means we're going to get -t minus 2t, which is t minus 2t. That's -t. There we go. Okay, so what do we get for an eigenvector out of that? Well, we can just make t1. That's simple enough. And we're going to get -1, 1. -1, -1, 1 for that. Okay. And so part A of this problem just wanted us to write down a basis for each eigenspace. We're in a position where we can do that. Okay, so let's write it this way, just to make it a little bit less writing. So we'll use the notation lambda for our eigenvalue, and then basis for E lambda. Okay, and so we had one eigenvalue that was just kind of scrolling up and taking a peek here, 3. And we discovered that basis, we need 2 vectors to get a basis for that eigenspace. Okay, and then the other eigenvalue was -1. Its basis, we just need 1 eigenvector. And it looked like that. Okay, so we've answered the question for part A. We're ready to move on to B, which was asking us, is the matrix that we started with diagonalizable? Okay, and so the question is, do we have enough eigenvectors? Okay, and notice that we do. We can look back at that characteristic polynomial again and notice we had a multiplicity of 2 for the eigenvalue for 3 and a multiplicity of 1 for the eigenvalue of -1. And we got the right number of eigenvectors, 2 for 3 and 1 for -1. Okay, so this is diagonalizable, and we should be able to write down our 2 matrices Q and D. All right, so we'll start with D, and again, that's just a diagonal matrix that has the diagonals down the main diagonal, or I'm sorry, the eigenvalues down the main diagonal. Okay, so 3 was repeated. Okay, so we'll start with 3 and then -1. Okay, and then Q was a matrix that had the eigenvectors in the right order as the columns. Okay, so we'll take 3, 1, 0, -2, 0, 1, and then finally -1, -1, 1. Okay, and I think we have finished.